LearningMeasure.tv, a science and engineering podcast with emphasis on measurement, brought to you by David Archer and LearningMeasure.com.
Episode 41, S-Parameter Measurements.
Hi, I'm David Archer, owner of LearningMeasure.tv and LearningMeasure.com. LearningMeasure.com is a subscription-based training website where when you register as a student, you get 1 week free. And then you, for access for the rest of the courses, it's $5 a month thereafter. I'd like to announce the following course has been added to the course catalog. Measurement 463, Introduction to Mill Standard 461 RS measurements. This is the fourth in a series of 4 courses on Mill Standard 461 measurements, and it completes that series. Okay, last time we started to talk a little bit about S parameters, and we're doing a short series on that. So the question might be, well, how do you measure those? And the first question is how might you measure reflection? So to measure reflection, you've got something going out, something reflected, something coming back. So you need something that can measure the power going in a particular direction. We're going to give an example of a device that can do that. There's other types of devices that do that, but we're going to do something simple. Let's say we have a waveguide. So you can imagine there's this square thing here, and there's another waveguide on top of it. Okay, so you put in a signal here into this waveguide, and it goes through. Well, if you drill a hole into the waveguide, there's going to be some signal coming in here, and then up through here, and then it's going to go this way and this way. Now, what happens close into the hole is extremely complicated, but you're getting a little bit away from the hole. And all you've got is basically the waveguide mode that propagates in the waveguide. That's all you have. Well, if you drill another hole between 2 waveguides, let's say the other waveguide bends up for just because, so we can measure it, and the other one goes straight through. Nothing important to that other than what I'm going to be drawing. Okay, let's say you drill another hole over here. And let's say that the distance between here and here is lambda over 4. Okay, so we got something that comes up here, and some of it goes this way, and some of it goes this way. Same thing as in this hole. Okay, but the difference is when this goes here, this one goes lambda over 4, and this goes lambda over 4. So when they're brought together, these are added together, and you get something that goes that direction. Well, now this one that goes this way goes lambda over 4 this way, and lambda over 4 this way. So this one's out of phase by lambda over 2, or 180 degrees. So when you add them in this direction, they cancel, so nothing comes out this port. This is what's called a directional coupler, a 2-hole directional coupler. There are all kinds of different directional couplers out there, but the main idea is in one direction, the signals will add, in the other directions, the phases will be arranged so that they cancel. So you have something that will, if you put in something at this port, it'll come out this port, and something come into this port, it'll come out this port. Okay. So if you're going to build yourself a reflectometer, you're going to measure reflection. And let's say this is your test port out here. Okay. You have some waveguide flange out there. And let's say up here, you've got something to measure your amplitude, A1. And over here, you've got something to measure your amplitude, B1. and you have something that measures the phase shift, the phase between the two signals. Okay. This can be anything. This could be a power measuring device, and you take the square root. So these things have to indicate voltage-like waveforms. So these could be power sensors. They could be anything. The only thing that's really critical is they're linear over the range that you want to make reflection measurements. We're going to talk about how you might calibrate this setup with only knowing that these things are linear and the phase is relatively accurate. So how, let's see, where was I? Yeah, okay, so we have this thing where we can measure A1 and B1. Well, we know that if you stick some load out there with some reflection coefficient gamma, that's going to equal B1 over A1, let's say these are magnitudes, times e to the I theta B1 minus theta A1, okay? So this is just dividing, this subtraction comes from this division. So this is the phase difference between them. So we've got the three components to measure reflection. So if this was absolutely perfect reflectometer, you'd put your one-port device out here with its associated gamma, and you would just measure this, and that would give you the reflection coefficient. Problem is, you never have a perfect device. What you really have is, you know, some of it's going to, this is not going to be exactly lambda over 4. So there's going to be some signal going that direction. There's going to be some signal reflected back here, regardless if you put any, even if you had a perfect load, because this is going to be imperfect. So we don't have a perfect test setup. Well, what do we have? Well, you can model you could model this reflectometer using S parameters. So, you know, basically how this works. At this end, you know, you're going to put in some sort of, you're going to have some sort of source. The reason why this jump in the video now is when we looked at the second half of the a little podcast on one ports, we decided to redo it because it was hard to see what was going on. If you remember, we talked about a coupler. And a coupler could be modeled. Well, of course you remember because you were just watching it. The coupler can be measured as a two-port. It's modeled as a two-port. Where is it? Okay, so we put in some signal here, A1, and we measure some signal here, B1, and what we talked about, well, measuring the amplitude and phase difference. Well, then you put an unknown load out here, okay. And I emphasize this two-port represents the reflectometer. So it's a series of errors. If it was perfect, this would be 1, that would be 1, this would be 0, and that would be 0. And then your reflectometer would read perfectly. But that isn't the case. And it also takes care of the calibration of whatever you're using to measure it back here. And we're going to assume that we're measuring actually amplitude of A1, the amplitude of B1, and the phase difference between them. Okay. So, and we're going to, the measured S11, or the measured gamma, we'll say, from last time, is going to be equal to this S11, whatever reflection is there in the coupler with no reflection actually present, plus S21, S12 gamma, whatever this gamma is out here, over 1 minus S22 gamma. So this is true. This is what you measure. Now, gamma measured is going to be in all cases is going to be B1, magnitude of B1, magnitude of A1, e to the I, theta 2 minus theta 1, where it's anyway, this is associated with A1, this one's associated with B1. Okay, so how would we calibrate this thing? Because this 4-port represents errors in the reflectometer. Well, if you look here, what happens if you put a perfect load out here? Gamma equals 0. Well, if gamma equals 0, this term is 0. Gamma measured is S11. So we put a load on the thing, and we're going to assume that that's perfect, reflectionless load. Then your measured gamma with the load is S11. The only thing you're measuring is the reflection that's inherent in the reflectometer. Well, what do you do next? Well, normally, to calibrate these things, you could, in fact, that might be all you do, but you probably would do more than that. Well, you put the next thing you would normally do is put a short on this end. In the case of a short, this is gamma load is 0. In case of a short, gamma is -1. Okay, what happens when you put a short on there? We already know S11 from putting on the load. Well, so we can subtract that from this, and we can get that for the short, gamma m short minus S11 equals S21 S12 minus over 1 plus S22. Well, did that help us any? Well, it kind of does, because if you want to look, if you wanted to look at this term here, we're assuming that this is small. If that's not small, then this reflectometer is a bad reflectometer. So, what do? Well, it turns out that S21 minus S21, S12 over 1 plus S22 is approximately equal to minus S21, S12 times 1 minus S22. Okay. So, what does that do for you? Well, if you assume, first of all, if you assume this is small, maybe assume that's 0, that gives you this loss, this term here, this S21, S12, the loss into the reflectometer. Well, that might be good enough. So now you know from an open you can know what the reflection is under no reflection in the reflectometer, and you can know what the losses are in the reflectometer, assuming this is small. But you don't actually have to assume it's small, because another thing you could do is put what's called an open on there. An open has the gamma open equals 1. Well, what does that do? Well, it changes all these signs, right? This goes to plus, this goes to minus, this goes to plus, and this goes to plus. So, what happens when you take gamma short minus gamma open? Okay. Well, you're going to get this equals minus S21 S12 times 1 minus or 1 plus S22, right, minus S12, S21, 1 minus S22. So by taking their differences, these are the same, so you're going to get, you can factor that out. And so we get minus S21, S12 times 1 plus 1 plus S21 minus, or S22, sorry, minus S22. Well, this is equal to minus 2 S21 S12. Okay, well now that helps a lot. So you can get this combination, which always appears in here, by taking this difference and dividing by -2. So that gives you S21, S12. So we can get, from all that, we can get approximately S21, S12 equals, right, the gamma short minus gamma open over -2. Okay. Oh, I should say measured, right? Measured. Okay. So just by taking the difference of that, you've got the loss terms. Well, what happens if you add them together? Well, you get something like, that's where you can get the S22 term, although it's probably not the best way of doing it. And I emphasize this is just one way of doing it. There are other ways. So now you look gamma measured S plus gamma measured open and short. This is going to be minus S21, S12, 1 plus S22 plus S21, S12, 1 minus S22. Okay, so now what you have is this equals 2. If you want to do the math yourself, this term cancels that term. These terms add together, so you end up with minus 2 S12, S22, S21. Well, so if you do this combination, you get S22 equals basically gamma measured short minus gamma measured open over gamma measured short plus gamma measured open. So by doing these 3 measurements, putting an open, a short, and a load, we've solved for all the parameters that are in our model of the reflectometer. So that gives you the calibration of a reflectometer, a basic 1-port measurement device. Well, we have a little time, so maybe we'll go on to 2-port. Similarly, you can measure this is a 1-port reflectometer or a 1-port network analyzer. But what you can do now to make a 2-port network analyzer is you just put another coupler with its own error model as a second port. So we'll put a 1 for this S, and we'll call this S112, S212, S222, and S122, okay? And then we'll measure in the same way. We'll measure B2 and A1. Well, we know how to measure these combinations and those combinations, but what you don't know, when you hook something, you have to do one more thing for a network analyzer. You got to do a through connection. When you do that, for this direction, you're going to get a measurement for going through that way from last week. Is S21 measured is going to be S121 S221 over 1 minus S221 S112. Okay. Similarly, S12 measured equals S121 S122 over 1 minus S221 S112. Well, you know this from your calibrating each side is one port, so you can solve for what these combinations are. But whenever you're measuring a actual device, whatever you stick in here, this combination will always appear and this combination will always appear. So once you know this value, you can stick it into the equations for calibrating out a two-port. So there you have it in a nutshell. Calibrations of a one-port reflectometer or a calibration of a two-port network analyzer. In this case, a vector network analyzer, because we did everything complex. That's all we wanted to talk about this week. As always, if you have any questions that you want to ask, send us an email at questions@learningmeasure.com. If you have any suggestions for an episode, send us an email at suggestions@learningmeasure.tv. Sorry, or I said learningmeasure.com. That'll work too. Or you can, if you are a vendor and you want to be on the show, send us an email at vendors@learningmeasure.tv. Also, we are now on Twitter at twitter.com/learningmeasure. We will be tweeting off and on when we're doing stuff and building new things and working on new courses. And we'd love to, if you want to tweet at us that way and tell us what you want to do, that's fine too. That's it for this week. See you next time.